Hi friends, I'm Utkarsh from IIT Roorkee, and today I will be presenting you in a nice way the Fourier transform and its applications in day-to-day life. Fourier transform, you would see that it is a simple tool, but without it, the technology that we see today wouldn't exist. So I would just go on with my explanation by first explaining you the definition and the idea behind Fourier transform, then from its pretty history, and then we will go to main part and most interesting part, its application part.
So let's discuss about the main topic. What is actually Fourier transform? So Fourier transform is actually defined as a mathematical tool to convert a function or a signal from one domain, a time domain, to frequency domain. You can take Fourier transform as a magic machine which takes complex function, complex signal, what you want to say, to simplified other signal functions, and this function the Fourier transform take its sinusoids. So what actually Fourier transform does, it breaks the signal, complex signal, into its constituent sinusoids. Means it actually says in that a signal like the last one is square wave. Square wave can actually be denoted by some of infinite number of sinusoids. Each sinusoid called harmonics. So in this diagram also you can see very clearly, like we have actually demonstrated that this is the square wave, and actually this is time. This is one side is time domain and other side is frequency domain. All right. So let's continue. To demonstrate the idea much clear, I just worked out and make a MATLAB program to work it out what actually is Fourier transform. So I just made a brief like code, and illustration is this. So I just add like then I add one more wave. First I made first simplified wave or a constant. Then I added up the first harmonic, then pretty more, then pretty more. At last, what you can actually see is if I add just little number of harmonics or sinusoids in my function, what actually is happening, that the my actual uh, what to say, superposition of sinusoids is actually giving rise to my original signal to very significant proportion. Let's deep dive into history of Fourier transform. So, in 1804, a French mathematician named as Joseph Fourier was working on heat equations. How to figure out heat equations, solve the equation of heat equations. So, while solving it in his renowned paper, research paper known as Analysis of Heat, he figured out that any function could be broken down into sinusoids or trigonometric series. That was a way of discovery that marked the landmark in mathematics and physics. And now let's discuss the application of Fourier transform, our main topic. Fourier transform is one of the most and crucial element in Fourier image processing, computer vision. So, in brief, just two important process I would discuss. There are much more in image processing that has dominated by Fourier transform. Let's see. Fourier transform is much has important part to play in optical character recognition. How? Let's see. If you take a letter A, suppose a letter and written by two different persons, and if you take Fourier transform, it would be too similar than the Fourier transform of other letters written by the same person. So by that way you can identify the character written in you can actually do character recognition. Then second property, second application in image processing, what we can actually do by Fourier transform is image filtering. Different image filtering process, Fourier transform is extensively used. How? Just take for example this first image being blurred by black lines. How can we filter that image? We can filter it that image by, if we take this for a sake, take Fourier transform of that image, we could figure out that what frequency that does the noise in the image 2D image lies in, and then by passing it in through low pass filter we could actually filter out our original image, like at the seen at the last. You guys must be excited to know that Fourier transform is also used in music industry. Extensively used. How? If you take a audio signal, sound wave, and you can do with one thing with Fourier transform, that if you can convert it into frequency equivalent and compare different tunes and choose the best tune according to what you like the best. That's one way. But the most prominent used that I think in for audio means music industry is its storage. Uh, the simplified storage we have in today's world for audio waves couldn't be possible if we hadn't have Fourier transform in our today's world. How? MP3. All of you must be using for your like audio songs, music. It actually uses fast Fourier transform for its work. How? Uh, it actually takes your audio signal, your sound, and convert into its frequency equivalent domain, and then it sorted out which frequency is actually prominent, and take only those frequency and just garbage out rest of all. Our eyes, ears are not at all susceptible to that much frequency change, and by that process you're gonna save a lot of space. Just suppose you are like a businessman and you want to just upload audio files into the web. So your first priority would be to save space. So you would go to for MP3, not for recording, because recording would contain all the frequencies and that would increase your space and the speed of website. So it it is also hugely used in medical research. Oh, amazed! How? Just I read an article. It says that what neurosurgery or neuroscience we are doing with the brain, with actually pretty much using Fourier transform for like studying the brain waves. First aspect. Second aspect, we are actually just I read a research paper on the Fourier transform use for understanding the structure of protein. By Fourier transform and different methods, we are today actually predicting out that this must be the structure based on the biomolecular interaction signals. Amazing, no? Fourier transform at last is very important in signal processing. It is the main part in signal processing. So why Fourier transform is so important, so super duper important, are main part of Fourier image processing. Three properties. First is convolution property. Convolution property says that if we multiply two signals in frequency domain and take convolution of same signal in time domain, these are two same equivalent. We done equivalent operation. So we actually do the fast convolution by Fourier transform. Second property is its sinusoidal basis is eigenfunction of differential equation. By this, we actually work out to store complex signal in simplified version. Third, it is extremely easy and fast to calculate the first Fourier transform by methods such as fast Fourier transform. Then, the first important application that I could figure out by reading different research paper was first. It is used in filtering technology, filtering the signal that we receive. Just for a sake, if you work a telecom company and if you send a signal from one end to another end, the noise between the signal is 100% sure. How to eliminate the noise? You can do one thing. You could take Fourier transform the signal and see where the noise come, and by passing it to low pass filter just as image, you can actually work out to filter the original signal. We can get original signal. It is extremely important in communication. The second important application of Fourier transform that I could find out is in modulation and demodulation. Suppose you want to send signal via media or for telecommunication reason. You cannot send direct signal. It would distort. So what we do, we modulate the signal. And for modulation, we actually have to set parameters so that different signals do not actually overlap with each other in air. How to do it? We have to set the parameters, no? How to set the parameters? So by taking the Fourier transform signal, we could actually figure out what carrier wave to take, what actual data information carrying wave to take for particular wave, what carrier wave to take, so that no two signal actually overlaps. Third main important that I found is it's important in sampling technique to sample the signal. Suppose you want to convert a digital to continuous signal into discrete signal or digital signal. How to do it? For practical example, you want to convert a recording, a voice, into digital audio file. How to do it? By sampling the signal. Now, if you sample the signal, you somewhat want your signal that it wouldn't distort, so that later you can convert it back into continuous, or you want your audio file to again convert into voice by listening it. You want it, no? So how to set the parameters? Same way, you can what we actually could actually set the parameters for sampling the signal. Like in sampling, if in brief, what actually happens, we set our main signal and impulse signal, and we do not want actually the signal to overlap with each other. So by taking the Fourier transform it and converting it into frequency domain, we could actually work out so that no two signal overlaps. The fourth aspect of its application in signal processing is multiplexing. Multiplexing is defined as method by which different audio, analog or digital signal could be combined so that they could be shared in uh, a single media. If we had scarce resource, how to work it out? We have to have multiplex. Like in your mobile phone, you have while processing in mobile phone, we have audio signal, video signal, and we have different type of data going on. How to work it out? We have really scarcity in mobile phone. We can't have different wires for different signals. So we want multiplexing. So for multiplexing, we do not want actually to data again to overlap with each other while multiplexing. How we work out? Again by Fourier transform. we actually set the frequency, the carrier signal in such a way that we adjust the carrier signal in such a way that they do not overlap.
This is the list of references that I have used.
Thanks, guys. Hope you like it.